right, so like I said, we're going to be talking about linear regression really throughout the rest of this week. And the next like 3 study groups are going to be focused around linear regression. And basically the idea of linear regression is going to be a prediction basically from like features and stuff. So this is going to be a little bit different from like inferential statistics that we just looked at. But I will tell you, I probably won't go into full detail, but there's actually a connection between the two. And the real connection is actually that t-tests and the ANOVA tests are actually just variations of what we call the general linear model. And basically that's where regression comes from. So it turns out that we can actually use some of the properties that we learned from a p-value, a t-statistic, the f-test. We can actually use that to when we do our linear regression, which we'll kind of see maybe in the labs, and I might try to show you guys that today. Okay, so I'm going to start sharing my screen, but before I do that, just kind of give me a thumbs up. Who's like done linear regression like from maybe back in like, you know, university or something like that? Okay, I see some thumbs up. Awesome, cool. So that's good. I don't expect you all to like be like masters of it, you know, because you've done it once before. But I think, you know, being a little more familiar with it, you know, can probably get an idea. I might kind of like phrase things and maybe you just never thought of it in this way. So we'll kind of see how that goes. And in phase 3, we'll actually be going into more like focusing particularly in prediction and usually classification, but the idea of machine learning. And I like to like really use linear regression as kind of like that introduction, because linear regression is relatively like easier to understand like how it's working, I think. But the same concepts will apply when we start looking at other machine learning models. Okay, so this is kind of like me kind of giving it little motivation of like, you know, what we're doing. And we call it statistical learning. And what we're trying to do basically is just find relationships. And like, if you can imagine, if you can find a relationship on how the system works, you can make some predictions, right? It's like, oh, if it only rains when there's clouds outside, you like know like, oh, well, if there's no clouds outside, it's not raining, you know, assuming that relationship is true. And that's kind of the idea of linear regression and any like statistical like prediction, right? It's like, oh, if this is true, you know, this is likely true. Now, there's some other factors in there too, right? That like maybe that are going to affect your actual prediction. And basically, the more factors you take into account, the more likely you'll get a better prediction, right? Hopefully that makes sense. It's like if the more information you know, the better predictions you can make. So that's kind of idea of like linear regression. So kind of motivating first from even covariance. So do we all recall like for covariance, it's like variance, but like across 2 different random variables. Remember, variance basically is the measure of the dispersion from the mean, right? So this is the formal calculation that you would do to find variance, right? Sigma squared. To find covariance, we're basically seeing how those 2 variables relate to each other, right? So if you look very closely, if you were to expand out this exponent, the squared, right? It's like you could replace this y with an x and you get variance. So in this case, we're combining those 2 together, and you're basically saying how do these vary from each other? That's kind of the idea of covariance, right? So we've seen this before, feeling pretty comfortable, right? One thing about this is that we have positive covariance, which means that those 2 variables, x and y, they correlate together. When x increases, y also increases. If we have a negative covariance, correlation correlates inversely. So as x increases, y decreases, right? So that's still a pattern, right? If we have no pattern, what kind of covariance would we expect? 0. Yeah, good. Okay. I used to, my professor back in like physics would say like when he was going through school, there was always the 1 or 0 guy. And it's like, if you were never sure, like a professor ever asked a math questions, like, you know, what do you think it should be? Usually 1 or 0 is the right answer. And that's kind of trickier. So there's a little note here that I put here is that covariance ranges from negative infinity to positive infinity. So it becomes harder to judge like what is a stronger relationship, just because there's a huge wide range of like you can kind of imagine it getting stretched out to infinity. So it's a little hard to compare like, you know, one covariance to another covariance, but this still holds true where we have a positive covariance correlating together, negative covariance inversely, and then a 0 covariance or close to 0 covariance would be basically no relationship. Okay. That's kind of like our first like tool, right? Our next one that we've seen before is correlation. So the classic one is Pearson's correlation, this lowercase r. And again, you might look at this like, oh, this looks like, you know, like super complicated. But if you look at it back to the covariance, you can actually see some really similarities for the x minus mu, y minus mu. So you can see how those correlate together. But instead of counting over like basically the average like distance from each other, essentially we rescale it by saying another, you can almost think of it like another variance within itself. So you can kind of see like basically it's very similar to this going on here. But what's nice about this, because of the scaling factor underneath here, it actually normalizes to -1 to 1. And we still end up getting a positive correlation, a positive R to be a, positive R being like a correlation that X and Y are coming up together. As X increases, Y increases. And a negative correlation meaning that as X increases, Y decreases, or vice versa. Okay. So typically we'll talk about like Pearson correlation, especially when we're looking at stuff. There's a really great diagram. I think this actually comes straight from the curriculum. You can kind of see here is like a perfect positive correlation where basically like every time X goes up, Y goes up the same amount. And then you can see like as usually you'll see like higher positive, like this is very like unlikely to get 1. But as we get like higher positive or even a low positive, you can see like it's generally true, but not quite all the time. And then we get 0. No correlation, basically completely random. Typically, you'll never get exactly 0. You'll get something very close to 0, and you have to determine like, oh, that's a very low correlation. And then we can see here, low negative, and then up to perfect negative. And I like to say too, is like negative is not a bad thing. Negative correlation just means you have the pattern figured out. You just have it in the wrong direction. So you might think of, instead of saying X and Y, and you have a negative correlation, do X and negative Y. Okay, makes sense? Cool. All right. So it doesn't seem too scary, right? Pretty easy stuff. So again, kind of going back to statistical learning, which is really what we're talking about here. And really when we're talking about machine learning, it's talking about statistical learning. So some basic stuff. So it's kind of important to know, and this is stuff you might have already like learned at some level. There's like variables come in 3 different flavors. There's the independent variables, the dependent variables, and the controlled variables. Now I will say is that technically there is like maybe like a 4th variable you can call like conflicting or confounding variables. And those are basically variables we haven't, kept in mind, right? So they really should come in these 3 different flavors. So if we're doing a good experiment, we'd have all controlled, but sometimes you might have some confounding or conflicting variables that basically are things that you just are not measuring. So whenever you hear the word model or statistical model, and you'll hear model a lot for like the near future and probably throughout your whole data science life, really just think of a function mapping or a function. In math, we call it mapping that defines a relationship. So the idea is like, if we have a model, we know if we put something into the model, what will come out. And basically you're mapping from X to your, well, I should say X, but like your features to some output, and we'll call that the target. Okay. So a very simple one, this is a linear regression line here, is that we have height and weight. And the idea here is we have a model that says, well, if you're a certain height, we predict your weight to be a certain value. So maybe this is like in pounds, for example. This height is in like inches or something like that. We can kind of see it's like, oh, if you are 60 inches, we predict you to be about, like 95 pounds, or maybe this is in kilograms, like 95 kilograms. Okay. And you can see here, this is the line right here is the model. Basically, we're saying, okay, this is what we predict things to be. But you can see obviously that there's some fluctuations between here. These are the little dots right here. Those are the actual data points that maybe you measured. And so you can kind of think about this. It's like, I want you to think about like when you have this model, it's like, okay, we have the height, we can predict the weight. Why would our data points be slightly off that model? Like what could possibly be causing that from like a real world standpoint?
What was the question again?
Yeah, maybe I can phrase this a little bit more direct. If we have a model that says we predict the weight by saying, oh, I know what your height is, I can predict your weight, why might that sometimes be off?
Maybe there's outliers that's possible. That's kind of outside the like average.
The variance is large, or
Yeah, I think you guys are actually going very technical, which is kind of good. You guys are thinking those terms. From a simple standpoint, if no one knows statistics, you'd be like, oh, because people have like different body shapes and stuff like that. It's not purely about their height. Not everyone has the same body shape. I'm gonna throw some really random stuff. Maybe someone puts on all their clothes in a winter jacket when they go get weighed, and versus like someone who strips down to basically almost nothing and gets weighed. Like that would be a factor too. Maybe men and women have different density of like fat and muscle and stuff like that. So the shape, their height doesn't necessarily define. You can't compare men and women directly. Maybe that's a factor too. So basically, like what this is saying right here is that your model is predicting this, and those data points are off because there's some other factors that we're just not accounting for. Okay, and so for linear regression, we'll see. Well, I'll talk about simple linear regression, and technically the chapter in like the curriculum is a simple linear regression, and then the next chapter is multiple linear regression. Really, no one really talks about simple linear regression. Usually you're talking about multiple, because multiple just means that you're factoring in multiple different factors or features, to make your prediction. Okay, does that make sense to people? Cool. All right, so I kind of want to drill in your head a little bit and kind of like plant a little seed in your head, is that when you see these points that are off from the model, you should think about like there's some other variation that we're just not accounting for, that the model isn't accounting for. Okay, cool. All right, so now I'm going to give you some terms and stuff that you'll hear a lot. So first of all, we'll talk about parameters to build a model. So those parameters are basically like, how do we actually say what the model is? So for linear regression, it's actually very simple, because the equation that we can state are literally like the parameters going forward. So we'll talk about like the weights of the features and stuff like this. And other models a little bit harder to talk about parameters. We'll talk about something called hyperparameters, which again, phase 3, don't worry about it yet. But parameters, you can think of like the parameters are things that define the model. Okay. And then we have things called features versus targets. So features are really like the factors, the independent variables that we're putting in for a model to like digest and figure out like, what's the outcome. And so, okay, we have all these different features. Like, let's say, for example, your outcome is weight. And you're trying to say, okay, we can measure the height. We can measure whether you're male or female, what age you are. Maybe that changes in your density of like, like how much your body weight or something like that. We can also say, like, are you, how much clothes are you wearing? Like that could also be a feature, right? So the idea there is that you're putting all those features in together, and that's what we call as features. And then the outcome we call the target. So that's basically the dependent variable. So you usually hear people talk about features and then targets. And you can kind of think of this as being like the X, the independent stuff, and this target being the outcome, the dependent variable. Okay, does that make sense, people? All right, cool. And then you'll hear model validation. So model validation, I think we can go into more detail if we have some time. Actually, one of the first lessons in topic 18 is about model validation. This ends up being really, really important, because basically you can draw, how do I say this? It's kind of like if you have the answer key already. If you have the answer key, you can develop a model based on that answer key. But it doesn't necessarily mean it's real life, or that your model does a good job explaining the world. I'm trying to think of a good example of this, like that's analogy wise, but you should really think about being that we have to be very careful about what we use to build the model, and then what do we use to make sure the model is working. And we'll do something called splitting that data into a training set into a testing set. So the idea there is that we will use the model, we will take the model and we'll figure out the parameters based on this training set. So basically it's some subset of the total data we have. And we say, okay, here's all the examples we want to use. Now build a model that's going to fit well with these examples. And we build a really good model, or the best model we could possibly get. And then we say, okay, now we have some new data, that your model has not looked at before. Basically, we haven't considered in designing the model, and see how well does the model perform in predicting those outcomes. Does that make sense? So hopefully that's just like it seems a really simple thing, but it is something that can be kind of troublesome if you don't take into account, because if you take in all the data and put it into your model to make the best model it can, well, your model is going to do the best it can on the data that's available. So the problem is you can't really test on like how well the model performs on data that's never seen before. And so the way I kind of equate this is like if you were, you can think of like back in school, like where you had like a practice test, right? And then you had like a final test. If the practice test was literally the same as the final test, you probably expect the students to do pretty decently, especially if they can kind of like really study the practice tests and then like study and then actually do the final test. And then you could probably reason say, you know what? I don't know if the students really understand the test. It's just the material. They just memorized the questions, or they understood like how to answer the question, but didn't really understand the material. So if you had a new question on there, they might be completely oblivious. Like, I have no idea what I should answer it to. So the idea there is that we have a practice test that is different from that final test. And I like to call like that practice test is the training set, and the final test is the testing set. Now there's also one extra part in here that I'm not going to go into details right now, but we will touch on it, is something where you have a practice set and you have a final test, like your test set. So you have your training set, your test set, and there's something in between called a dev or validation set. And you can think of that validation set, I won't go into full details here, but almost like kind of like your own practice tests. So you can kind of imagine like the teacher gives you like, oh, here's a practice test, which is your training. And then you're going to have your final test. And so you kind of like, well, I want to like, you study the practice test really, really well. And you're like, well, I want to see how well I think I actually know this material. Like how well do I generalize this knowledge to answering for the final test? So you develop a dev test or a validation test and like a little mini practice test that's a little bit different from your training and just see how well you do there. And that's what we'll do. We'll kind of reiterate over and over and over again. And then we'll finally do our final test where it basically says, all right, how well does this model actually know this information or make these predictions? Does that make sense to people? Give me a thumbs up if that made sense. Okay, any questions at all? Okay, cool. And I'll go into details of like how this actually works, but just kind of know. Last thing I want to throw out there, and this is technically not going to happen really until phase 3. The way we evaluate how our model does is we use something called a loss function. And that actually turns out to be really important in machine learning. And really, really short, like why machine learning, like why that's really important in machine learning versus like linear regression is linear regression. We define the parameters. In machine learning, the computer algorithm defines the parameters by seeing how well it does based on this loss function. So this loss function is kind of like saying, how well does the model predict outcomes? And so that's going to be like, that's obviously important for any model, but it's going to be really important for machine learning algorithms because the machine learning algorithm, not so much linear regression, but other machine learning algorithms, phase 3, will try to optimize to make this loss function, make the loss as small as possible, we call it, or minimizing that loss. So just kind of something to keep in mind. But basically, you think of this loss function, just think of it when someone says loss function, you can think like how we evaluate that model, how well does that model do? Okay. Cool. And those are the main terms I really wanted you guys to focus on. So that'll make sense? All right, cool. Sweet. I am recording this, right? Okay. I couldn't remember if I pressed record, but I remember doing that now. All right, so let's go into actual linear regression. So we always, again, see data points in regression. So you should really look at like the regression line being like something that's trying to predict what these outcomes are. And you probably in reality, like you can see this like kind of scatter across. The thing is that this line right here goes through these points and not just like, in a complete even direction, right? It roughly predicts what these data points are doing, okay? So kind of exploring motivation. It's a way to model the data, basically, right? And the reason why we're doing linear regression is, first of all, linear, think linear, like line, right? Is that it's relatively simple. And so it's a really easy like data science go-to. Like a lot of people will go straight to data science, linear regression and call it a day there. We can talk about really advanced models and stuff like this, but sometimes it just makes sense to have linear regression because a lot of times you might already have a theory of like how the data should be structured. So if you're ever coming from like a science field, you probably have done a lot of linear regression because you already have a theory of how what factors into the results. And sometimes in data science, we might not really know what the full, like you can kind of almost imagine like scientific theory of like why these things happen. So what we'll do in the future, like path linear regression, is we might try saying, well, okay, computer, here's all the data, you figure out what the best patterns are. Versus linear regression, we're basically trying to define saying what patterns there are. And it turns out you can make linear regression like really, really good, but that really, really good means that you're filling in like an infinite number. Well, you won't literally go infinite, but you can get basically more and more features and more complexity in there. And it ends up being like actually very difficult to like figure out what things should you put in versus not put in, because then are you, we'll talk about this when we judge how well the model does, but it turns out if you put a bunch of features in for your linear regression is going to do something called overfitting, where it's going to be trying to predict something really, really accurately, but it doesn't really have that accuracy. A typical overfitting is like if you just like literally try to connect all these dots together, and it's like it perfectly fits on the practice data, on that training data, but if I have a new data point, it's probably not going to fit on that exact squiggly line connecting all the dots. Okay, does that make sense? Okay, I'm still talking pretty abstract, so hopefully that makes sense. Cool. I hear my Slack going off, I think. That's okay. I'm in meetings. All right. So this is where I love this diagram. I actually don't remember where I got this from. Oh, here's the actual link. But I love this diagram here because I think it sums up linear regression so well. And basically you can kind of think like, this is what we call simple linear regression, where basically you have one feature and one target. And what we're going to do is we're going to predict, we're going to develop this model in this blue line here. And we're going to use that model to help predict when we input an X, what is the response to the target. Okay, so the classic equation of this is y equals, and I'll put like a times x plus b. Sometimes you'll see this phrase differently, but if you remember back in like school, you probably learned it as mx plus b, same idea here. Later on, we'll actually have multiple x's, so we'll talk about what that looks like. And then what's cool is that the slope is simply r, which is the correlation, divided by the standard deviation of y and the standard deviation of x, which is kind of cool. It's like, oh, that's how you get a. And it turns out you can actually solve this really quickly, not just with, well, you can solve this really quickly with simple linear regression. And it turns out this is a closed form solution, which even when we expand it out to multiple linear regression, we'll actually see that you can always find the perfect answer. The real question is like, how quickly can you find this answer? Okay, so I'm going to kind of just walk through this again. You can see these green points. These are the data points. This is the blue is the model right here. When we actually build up our equation, which is basically the description of the model, we're defining a slope, and we define b, which is the intercept with the targets, like the y-intercept. And this, I don't know if you guys can see that red going from the green points down to the model. This is what we call our residuals. And basically, like in here, this diagram calls it vertical offset, y hat minus y. Y hat is usually when we talk about the hat, that's the model. And this y is the actual data point. So basically it's saying, hey, how different is the model's prediction from the actual data point, that would correspond to that prediction. And what we're going to do, we're going to take those residuals and use those to basically decide on, is our model doing a good job or a bad job. Now you can see for some of these data points, it does a pretty decent job. For this data point, it's very far off. So maybe there's a better model we can put in there that would better predict, or not better predict, but reduce our residuals to a smaller value. Okay. Does that make sense to people? Give me a thumbs up if that's making sense. Okay, cool. Again, if there's any questions, feel free to interrupt me, right? So the thing is like we want to check out, like once we have our model, we define it with essentially this y equals ax plus b. Okay, we need to find, is it very good? And again, that loss function. And that loss function is something called, like for linear regression, is the sum of squares. And so like sum of squares, like what does that mean? It's like, well, what we're basically doing is we're taking our distance from this data point to the actual model and taking that value. And in this case, it's showing like absolute value, but usually we square that value to make it positive, okay? And you add up all of the differences. So you add up this difference squared, this difference squared, this difference squared. So we usually call that the sum of squares, okay? What's kind of interesting though, is that this is where I'm like, technically, when we do something called, if we're going to use a metric called r squared, we don't actually measure it directly on the model. What we measure it against is actually against what we consider like the worst like model, but like you can think of it as like a very simple model. And a very simple model is just literally saying, hey, whatever y is supposed to be, just say whatever the average is. So if the average weight of this group of people is 55 kilograms, you just say, predict 55 kilograms for every single person, right? Regardless of their x, in this case, like if we went back from the weight being the target, height being our feature, then regardless of their height, just say 55 kilograms. Like that's going to be the answer. And that's just going to be a straight line. And that's basically, we're going to say, hey, how much worse does this, well, more in the sense we say, how much better does our model in gray here do than this orange model, which is just the mean? Okay, does that make sense to people? Okay, and the reason why we do this is just basically, you can kind of think it's like amount of effort. If it's like, hey, if it's relatively random or if it's normally distributed, you can just guess the average because basically there's no way to really know except for just guessing the average based on these features. So the idea there is like, if we can predict, we can tease out some extra information with this model, then we want to know how much better it is from just guessing the average. Okay, cool. So one thing you'll see here though, is that we have some data points in this clearly quadratic form, right? And you can see here, our average model is going to be here. And the thing about this though, is that you can probably see like, is there any way to draw a straight line that's going to do a good job predicting these points? Probably not, right? Like, you can maybe get some, like if you like ignored everything less than, in this case, less than 0 on that feature, you could maybe get a good decent line, but you can never get like all of these data points in a good line. And that actually goes to a good example of like, when does linear regression actually work? Like, when should we use linear regression? And I will tell you is that we will talk about ways to modify linear regression over the next couple study groups. So even though it's not linear, so we'll talk about like linear regression, but it's more like a modified linear regression. There's actually some tricks and stuff like that you can do to actually do a pretty good job predicting something even like this. Okay. Cool. So I'm going to go into the assumptions of like when does linear regression work. So the first thing to do is this. I love this little diagram right here. So you can see that these are the data points in blue, and red is the linear regression line. So here, if you're looking at this and squint like this, let me ask you, is this a good model?
It's pretty good.
I mean, in general.
It seems a decent job, right? Like it's at least following that shape, right? So I will tell you is that after going through these numbers, you will find that this is probably not, there's something else going on here. And we'll actually have to modify this linear regression to actually make this work, or give up on linear regression and do something else. And what I'm going to point out to this is there's a couple of things. One, it looks roughly linear, but the big part that probably stands out is the small values right here. You can probably see is that of these small values, the linear regression is just not going to perform very well, right? It's always going to overestimate the actual data points. You guys see that difference? Mm-hmm. Yeah. The other thing too is that as we move forward, you actually see a little bit like, these values right here are pretty close, right? Like they're not too far off, but as we get to further values out here, you see that the difference is actually much, much larger. And that's a cause of concern. But basically you can think it's like it's splitting in the middle here, but like these points are not going to be exactly right here. They're going to be much more spread out. And that's going to be an issue too that we'd have to address. So these are the kind of things that you'd like want to check out for linear regression. Now, the good thing is you usually don't draw out your linear regression and then say it was a good model. You usually try to look at the data first and then determine, okay, will my linear regression model work here once I apply it? Okay, and that's what we're going to go through. So the first thing is it normal? So this is kind of a weird one because I think I want to make this really clear. It's not that you can't predict normal data or non-normal data. And you guys, by normal, I mean like a normal curve, right? What I mean here is actually that when I say normality, I'm talking about the residuals. Do the residuals go across spread out normally? So you can kind of think about like if I took my linear regression, would I have residuals that would actually be spread out normal? So you can kind of think of it as like, if my model is doing really well, you would have close to 0, like the residuals are relatively small, like close to 0, right? And then sometimes you might have some outliers and stuff like that that go off to the side. But if your residuals instead look something like this, where you have maybe a trailing out tail, or maybe something that's not quite normal, which we'll show a couple of examples, it might mean that your model is just never going to be able to capture that complexity in the data, okay? So a classic one of doing this is using histograms and Qq plots, which Qq plots are actually using the CDF. So we have run the cumulative distribution function. But our histogram here is like our typical, think of like our PMF or a PDF even. And our Qq plots, has anyone heard of a Qq plot before, by chance? No, not so much. It tends to be a little more niche and everything like that. So I don't expect most people to know this already. But basically it's a quick visual test. So essentially you take your residuals and you plot out these residuals and say, okay, like do my residuals look normally distributed? So you can see here, pretty standard normal distribution. And right here's my Qqq plot, which basically is your quartile per quartile. And basically you're plotting out the CDF on a diagonal line like this. And essentially what's happening here is we're just seeing, hey, do these values really differ from our expected? And you can see here it's like pretty good. And that's because we'd expect most of the values to be in the middle here, which is what we're seeing here. And then maybe sometimes there's some values that are falling off like more extreme sides. You can see here that's kind of up in here, but it's relatively close. This right here, we have the data that's really peaked in the middle, but then kind of falls off immediately. So like the data's like really, really close, and then there's some really extreme values on the side. And you can see like this is not quite normal. In fact, does anyone know what we describe this as like a high or low? Well, kurtosis is what I was trying to get at. So this is like a high kurtosis, right? It's like, oh, like, okay, like you have a very strong peak, right? These tails are very, very thin compared to the original here, okay? And you can see on our QQ plot, we would expect is that we'd expect all the data points to be along this line. And you can see it's like relatively normal in that center part, but then on the sides here, we can actually see that a very skinny tail, or very skinny tail, or not skinny tails, like this would be like technically fat tails. And you can see here, that's where we get these extreme values here. So those values aren't quite matching up to what we'd expect if it was normally distributed. Okay, and then you can see here there's a very skewed right distribution. In the same way too, you can see that like it's basically starting to fall off on those tail parts, where basically we have a very like heavy amount of data issue on the left here, which is what we're seeing here. And then on the right here, we'd expect the data to be smaller, but it's taking a little bit longer. So we get this extreme part right here. So these are kind of like quick visual tests you can do. Okay, does that make sense to people? How you check these residuals for normality? And again, it's not that the data is normal, it's that the residuals are normal. I want to kind of put that in there because sometimes people will go like, oh, my data is not normal. It's like, that's okay. Like your data doesn't have to be normally distributed. It's the residuals that matter. And what I mean by that is that I'm not going to draw them with Zoom because I know Zoom kind of did some weird stuff where you guys couldn't see it. If you imagine this line right here, let's say this line did really, really well, and I have a data point way over here, like off screen, like you guys see my cursor, right? Like this little point right here. That could still follow along the linear regression. And you might say the data is not normal because there's a huge like outlier essentially, like this very far off point, right? It's not normally distributed, but that's okay because the residuals are going to be relatively small and still normally distributed along this linear regression. Does that make sense to people? Okay, so another thing you can imagine is like, imagine this, let's see if I go with this one, this data right here, if I took out all this middle stuff and I had two clusters, one right here, one right here, but the linear regression does a really good job across both clusters, that's okay. That's still not like the data itself isn't normal, but the residuals should be normal. Cool. Okay. Any questions on that? No? Okay, cool. I don't have the chat here. Oh, go ahead.
I have one question. Can you go back to the scatter plot?
Say that one more time, Simon.
Can you go back to the scatter plot?
Go this one.
I am curious. Yeah. If we ignore this smaller value here, like after 50 or something, then it's pretty linear looking. But then towards this higher value, so varying. What like do you still like use like a linear regression?
Yeah. So from this point,
something else.
Yeah, from this point right here, I would probably say like if we ignored everything lower than 50, you probably would see the residuals are normally distributed, right? Is that you would probably like, even though these values are higher, like more extreme, right? There's hopefully less, like most of them are close right here. And these values, I'm kind of like assuming a little density here. It's like there's more density here. And then as we go further out, it's less dense. You would see a normal distribution of the residuals. But that's only one assumption, which is why kind of like we'll go through a couple ones. And this one's going to fail on the next assumption called heteroscedasticity, which is a mouthful. So that's kind of what I'm getting at next, if that makes sense. For the record, kind of fast forward, like what do you do if you have a distribution like this? You're like, I want to predict this. What you would probably do is you would transform the data by essentially like, instead of predicting on, in this case, like number of TVs, I'm going to say like number of TVs and how many sales there are. I don't actually remember what the data is. But let's say I have this feature here in this target. What I'd probably do is instead of predicting over what's it called? This feature, I would probably do a log transform. So what would happen is I would punish these more extreme values. And I'd actually, instead of predicting on like, let's say number of TVs sold, I'd be predicting on the log number of TVs sold. And that would probably be closer to actually doing a linear regression that would make sense and still follow those assumptions.
Yeah, so you will still do the linear regression.
Yeah, I do the linear. I could still do linear regression. I just have to modify the data. You can think of either. You can either think of modifying the data or modifying what model you're using. In a lot of ways, they mean the same thing. Is that if we, in a lot of ways, like if you look at this really closely, this you can imagine a function that really does a really good job, like actually mapping out this direction, and that ends up being like, oh, that's probably like a log function, or at least some variation of the log function. And so you basically are saying, oh, when I do a log transform, you can think of it transforming the data, or you can think of it as like you're transforming what kind of model is going to be fitting on the data, but they actually are equivalent to each other. So,
Right.
yeah, good question. So, okay, so yeah, so this is where I kind of go into like the next assumption is heteroscedasticity, which is a huge mouthful. And I struggle on it every single time. I never know if I'm going to actually get to the end of this word by when I'm halfway through. But what we're looking for here is, again, in the residuals. And basically, we want to see, are the residuals evenly spread through the range? So you can kind of think of this when we talk about normality, we want to make sure the residuals, overall residuals, regardless of where they occur in the graph, are normally distributed. Here you can kind of imagine is that we, how do I say this? Is that the residuals, as we kind of like increase or decrease along the feature, does the accuracy of your model increase or decrease? So what we're talking about is something homoscedastic. So if something's homoscedastic, it basically means is that as we adjust as we go across the feature, the model does about the same, more or less, throughout the whole prediction, like throughout the whole range of the feature. Okay, does that make sense? So basically it's that like this would be heteroscedastic because as we move across X, our model does a pretty decent job and then gets worse and worse and worse and worse. So you would look something like this model would look something like this very first graph, which is heteroscedastic, where our residuals are relatively small. You can see relatively small. And then as we move across that x-axis, you see these residuals getting very, very large, which is what you're seeing right here. Okay, so that's what we're looking for heteroscedastic, if it's heteroscedastic or not. Some typical ones you'll see, like this is what you kind of hope for, like more or less random. And it's a visual test too, right? This is what this is. Like, okay, like is it more or less random? Like good enough. This is heteroscedastic. This is definitely like a strong pattern in there. Like sometimes you'll see a little less, like you can see like these straight lines. It might be less straight and stuff like this. It might be a little more fuzzy and stuff like this. And then what you'll see a lot of is like when you have something that's not a linear pattern. So you can't really model a non-linear relationship with linear regression directly. You have to essentially add some non-linearity into it. But you'll typically see something like, you can see these like lines here. Those lines are usually not drawn. There's just for emphasis. But you can see here is that like my zero residuals here, and sometimes it does really well, and sometimes it does really poorly. And that's where you can imagine if I had, kind of going back to here, if I had my linear regression line going through here, it does really badly here and gets a little bit better, a little bit better, a little bit better, and then worse, 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 worse. And then a little bit better, a little bit better, a little bit better, and then worse, 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 worse. Okay, so that's what we're seeing right here. Does that make sense, people? Cool. So
I have a quick question, Victor. Sorry to jump back. I know we were just talking about how the like residuals are normally distributed. I think I wasn't quite understanding that part. Is that like the values, or is that like the counts of? Is it like there's a residual for every value, right? But is it like the values of the residuals, or what is that graph that's like just a little bit up there?
yeah, so you're talking about this one right here, or like a couple of these ones.
The one at the top of the screen right now, like that
one?
That one right there. Yeah.
Okay, yeah. So this is kind of it's a little small too. Maybe if I open the image, I can zoom in a little bit. No, that doesn't really help because you can't see the axis. But you can kind of imagine is that these are the actual residuals, like the values of the residuals, like a residual of 0 or close to 0, right? That first bin. And this is the frequency of how often that happens. So like most residuals are relatively small, like looks like, like the frequency, I'm trying to look at 0.4-ish is on this about, which is about like a little bit less than 1, like maybe 0.75, like maybe from 0.5 to 0.75. That's a certain frequency of this value. And so basically what we're doing is we have all the residuals and we're basically just bidding, saying how often do our residuals, like what are the values of those residuals? If that makes sense. So like most of them should fall within, in this case, this means a pretty decent, model is that it's falling, most of them are within like, -1 to 1, so like pretty decent size. And then there's some that as we get further, as some values of residuals are going to be like negative or, more positive. So in this case, like -3, and it's like more +3. So that's just saying like, oh, there's few residuals that have really extreme, like the model did a really poor job of predicting.
Okay, gotcha. Yeah, sorry to backtrack. I just couldn't see like the axes and stuff. So yeah.
Yeah, I know that's a little hard to see on here too. Yeah, so that's kind of what you're looking at when we talk about residual. Like, I'm glad you brought it up. Like, don't feel bad for going back to. Is that I do think this one's a little tricky sometimes because I think we tend to try to remember the data being normal, but it's not the data, it's the residuals. So that's an important aspect.
Right.
Cool.
Yeah, thank you.
And just to confirm, are the those are standard deviations on the X, or are those the actual?
I think, yeah, these are normalized residuals. So I think they're actually dividing by the standard deviation. If I like from this graphic, like I know it's a little small right here, but like normalized residuals probably means like they take the residuals and then normalized it by dividing by the standard deviation of the residuals. So this would be like one standard deviation away from, you know, the average residual value. Which again, like you can kind of hear this now, it starts stacking on a lot of different, like the residuals are calculated from the data / model. And then we're looking at those values and seeing how they're spread out. They get a little more abstract, which I totally feel for you all if you're kind of like scratching your head a little bit, like, what exactly does this mean? It's a little tough to kind of put together, but I'm hoping that like, at least you guys can see where this happens. Because I think what usually I'll see from a lot of people, and this is not even like just students, this is like even people in the field, sometimes they confuse these concepts and they don't remember like how they're applied, but they remember it needs to be normal. And then like they'll say, oh, we can't do that because it's not normal. It's like, well, yes, you can. It's just kind of like, you need to look at the residuals themselves. So yeah, cool. Any other questions? This is good. I'm totally fine with you guys backtracking if you guys have other questions. Cool. Sound pretty good? Thumbs up, yeah. All right, cool. Sorry. So I just wanted to show real quickly, here I have the other notebook that's from the curriculum. So I'm just going to mention really quickly about like that training set and test set. We'll show a little bit of how this is done in practice, but just know basically the main thing that we're doing here is this model validation. And basically the idea here is we want to make sure that we something called like overfitting. And what this means is that like our model does a really, really good job on predicting the data that's given, but does a really poor job of what we call generalizing. Basically, it's like it's shown new data that's never seen before, and it does a really, really bad job of like actually making those predictions. And that's what we want to avoid. So one strategy is basically, and a very common strategy and very effective strategy, is to do something with model validation where we take our full data set. So someone gives you, say, hey, here's all the data we have. And you say, okay, let me just randomly put some of the data into my training set, which I'm going to use to actually build up my model. And then some of my data as a testing set essentially is to be like, hey, how well does this model do without ever seeing these values? So typical like splits are like 70-30, 80-20. I've even seen, depending how much data you have, you can get up to like 95-5. Like 95% of the data is actually on training, and then 5% of it is for your testing set. So it just depends on how much data you have. I would say 80-20 is a pretty safe like bet to have, like if you're not really sure how to split it off. Now note that is that the more data you do have in this training, the better your model will probably do. However, it also means that this test set is very, like, if you don't have a few examples in this test set, it might not be super, like your model might not actually do very well to generalize, and you won't know that because remember, you're randomly picking these out. So that's why we try to say we want the most data we can, because then we can get all those examples into our training set and actually do a good job of making a good model. But you want, what's it called? That test set too, it's like that balance. Like we want to make sure we have examples to actually test and say, hey, now that you've learned like how the model should be built, does it actually work? Okay.
Hey, Victor, quick question. You had mentioned that third test component, I forget what you called it. In some cases, how would that affect your percentages here? Would you hold out like 5% or 10% for that?
Yeah, good question. So it's usually called a dev or validation set. So depending on who you talk to, they'll call it a dev set or a validation set. I think the curriculum mostly calls it validation sets when we talk about it. And this is kind of like an internal like test set essentially. So you can kind of think of it as like, I like the analogy of like thinking of a student, is that when we have like, you imagine like you're a student and the teacher gives you a practice test or practice material. We'll call it practice test just because it's kind of worked within this analogy. And you study that practice test as well as you can. And then at the end of the year, you'll have the final test, which is kind of the test set here, right? And see how well you do. Well, you're only supposed to take the test set once, right? So take one final to really know if you understand the material, right? And you, the student here, are the model. So the thing is that if you just study just a training set and then test it, you'll know how well the student knows at the end of the like actual testing. But then it's like, what if the student is just, what's it called? Practicing, going over the practices over and over and over and over again and just memorizing those answers, and the student doesn't learn anything. So what you can do is essentially have like kind of like a practice final test. So it's like a test that's not going to be the final measure, but kind of like a way, a way for you to check if the student is actually learning from the training set or is just like memorizing those answers. So what that would look like here, it'd be something like if you had 80-20, you might have like an 80-10-10 split. So 80 being the training set, and then 10% going to a validation, and then 10% going to your final testing. And the idea here is a test that's done once, because if we kind of, there's a subtlety. It's like if you use a test set over and over, so let's say you have a model, you use a training set to train the model, basically develop a good model. And then you do the testing set and you're like, oh, you got like a score of 60%. And it's like, okay, go back to the drawing board, change the model, use the same training set, but use a different model parameters and getting a model. And then going against a test set, it's like, oh, you got a 75%. Oh, much better. The problem is that you are subtly fitting onto the test set without directly knowing the test set. It's kind of like saying you're hot or cold, right? It's like, oh, you're getting hotter, you're getting colder, right? That's essentially what's going on. But it's kind of like one step removed, and that can end up causing bias in there, where now if you put this out, we call deployment, we actually put this model out to the world, you might actually see this model doesn't perform very well in the real world because you've been overfitting on your personalized test set before you've deployed it out. And so that's the idea of this devs test. Is like what you can do is you can basically do your training, check out the dev test, like, ooh, didn't do very well there. Let's redo the training, new parameters on the training, and then check against the dev test again. Like, okay. And the idea is that you're kind of, in a lot of ways, using the training set as the dev test or the validation set as part of the training process. And so it's okay if you overfit on that, dev test, because you're still going to have that final set at the end. Okay, does that make sense? Okay, cool. I saw some thumbs up. All right, and again, we'll go into some more details here. So, tell you what, there's a couple of directions we can do. One, I can kind of like go into still a little more theory of like, for example, we can talk about a validation, see what that looks like, or we can dive into actually performing a linear regression and seeing like what that looks like code-wise. So kind of, what are your thoughts? And you guys can unmute, or I don't know what the easiest way to vote.
Personally, myself, I like, I'm very transactional, so I like actually seeing it done. It makes me understand it a bit better, but that's just me. I know other people learn in different ways, but me, myself, it's better for me to actually dive into the code and actually see it. I don't know how everyone else feels though.
Yeah, I like the coding also.
Okay, yeah, we'll go into coding. So let me go ahead and just bring this. I'm checking on my other notebook here, and I'll be frank with you all. Like, this is a notebook that's kind of in development, so I might not have it completely put together, but we'll see how well this goes. At least we'll be able to show you guys the code of like, how this would work. So one thing I'm going to do is I'm actually going to mention it as multiple linear regression. And all the difference you got to really know from multiple linear regression to simple linear regression is that instead of having one feature, X, to create, to predict outcome target Y, we have multiple features that come together to predict Y. Okay. And the way we basically say like, okay, like when at the end of the day, when we actually check out like how well your prediction's doing, you are using, what's it called? You're using those metrics for simple linear regression in multiple linear regression the same exact way. It's just that the features coming in are just, there's more of them. So this is where like the classic diagram, I don't like thinking of it this way, but I'm going to kind of present it in this method, is when you think of this equation, which is just going to look at, I'm going to show you, this is the equation right here. So you're like, oh, that looks fancy, right? And basically all it is this y hat is the model, is equal to, you guys can see this okay, right? Like it's not too small. Okay. This y hat is the model, is equal to, and these are all the parameters. So we have beta 0, beta 1, all the way to beta n. And beta 0 is just the y-intercept, or I say the target intercept, right? But you can think of the y-intercept, right? It's just a number. And then beta 1 times x1. x1 is one of the features. x2 is a different feature. x3 is a different feature after that, and so on, okay? This number right here, beta 1, is like what our a was. Essentially, it's just a number. It's a coefficient. We call them the coefficients, if you guys remember back in math terms. The coefficient of this term here, of this x1 term. So basically, this is telling us saying how much, strength, how much should we multiply the value of this feature by to add into the total model. Okay. Does that make sense to people? So if you're feeling like a little overwhelmed, just like go back to just look at this, like imagine it's just y hat equals beta 0 plus beta 1 times x1. Like that's just simple linear regression. And all we're doing is just adding new x1, x2, x3 features and so on. Does that make sense to people? Cool. All right.
What was the beta 0? So the beta 1 to beta n, that's like per x, how it's changing with the y, but what's the beta 0 again?
Yeah, the beta 0 is just like kind of like that y-intercept. So
okay.
You can kind of
Like
think of
b?
Yeah, it's like just a constant. It's dependent. It's not dependent on any features, if that makes sense. In multiple linear regression, like this is where like in simple linear regression, you can think of it like you're moving the model up and down, kind of like as its baseline. So sometimes people will talk about, like, especially if you're in science, starting the linear regression starting with 0. I don't know if anyone has heard this, but like, oh, always have the model start with 0. And in some cases, like, it doesn't make sense. Like, for example, I'm trying to think of a good example of this. But like if your x feature is 0, it's like you might not start with your target at being 0. For example, let's just pretend like a house, like if you're predicting houses and like, oh, if you have, how many rooms do you have, predicts the price of the house. Well, the more rooms you have, probably the higher the price of the actual home, right? More or less, right? What would it mean for a zero room house? Anyone got an idea of how you would interpret that?
I think that would be beta times x0, right?
Right, yeah, like in this
No,
equation,
beta 0 times x0.
yeah, it'd be like x1 is 0 here, and that's beta 0. But I meant more for like conceptually. Like if I said like, oh, if I have this equation where the more rooms we have in a house, the higher the price will be. What would we expect the price of a 0 room house?
The price of
0.
a studio?
0.
Price of a studio? Maybe not. Maybe that might be considered 1. I actually would argue is that a 0 room house is a plot of land. It's like, that's kind of like the starting off point. There's no improvements on that land. It's basically 0. It's like, well, you wouldn't say the price of a plot of land is 0, right? There's like some value inherently for that plot of land. So you would start off with a certain value, let's say, I don't know, $50,000 or $30,000 or whatever it is, right? And so, oh, that's my beta 0 then. My beta 0 is kind of like, if there was nothing on that, house, it's just a plot of land, how much does that cost? And then, as you improve the land, the price would go up as you add more rooms and stuff like that. Does that make sense? I know it's not a perfect scenario. I'm not a real estate agent, but like, I think in my head, that makes sense, at least initially. So you can kind of think that beta 0 as being like the initial, like if there's no features put into there. Yeah. Now, if you have this equation, this is where everyone goes like, what is this thing? Because if we just have beta 0 and beta 1, it's a linear line. It's just a line, right? It's like, what is it if we had beta 0, beta 1, and beta 2? Like, what would that be? Does anyone know mathematically what that would be?
That would be a plane.
Be a plane, yeah. And that's what this is. And then it's like, okay, what if we had not beta 0, beta 1, beta 2, but also beta 3? And you're like, well, then people say it's a hyperplane, which is a 3-dimensional plane in a 4-dimensional space. And they say, okay, what if we had like, 50 features? Like, oh, it's a 50-dimensional plane. It's like, in my head, I'm like, it's not helpful. It maybe help a little bit for some people, but I don't think it's helpful. I think of it as a bunch of dials. Every beta 0, every parameter is a bunch of dials that you're tweaking very slightly. And you're seeing if you can adjust that beta 0, beta 1, beta 2. And what you're doing is that if you tweak these things, outputs the target, like our predicted target is the y hat. And basically we say, hey, does this y hat work well for these parameters put in? Another way you can think of it is that each one of these dials is basically individually making a little linear regression line, and that we have to look at saying, like, you know, if you imagine having multiple like little linear regressions. So I wish I could draw. I'm going to see if I can draw and see if you guys can see this, because I think this would help. I hope this works. Can you guys see my blue drawing here? No, dang, I don't know. I don't know why that doesn't work. But you can kind of imagine is that each one of these dials represents like one little like linear regression like diagram. Like you can kind of imagine it's like one of these, right? And then each dial is independently changing like this line with different data. And then we have to collectively add up all the errors together to know how well it does overall. Okay, does that make sense to people? I hope. I wish I could draw on my screen. I gotta figure out what's up with Zoom, but that's the idea. So once you realize, like, okay, multiple linear regression, it's not that big of a deal, just adding new features, just new dials. First of all, you can solve this. Like there's a closed form, we call it solution, where basically you essentially look at all the features, and this capital X is representing a matrix of features. And basically you can use that to figure out what you can see B is a vector here, just all what the betas are, and you can solve this directly. And it's actually straightforward. Usually when we actually do linear regression solves, this is usually how we're solving it. So okay, it's like, okay, cool. We got this multiple linear regression part. How do we actually perform this like actual multiple linear regression? So let me make sure I get, first of all, my imports right. So let's get those in here. Oh, I do have, sorry, I had a little realization. Okay, this is our linear regression. And sorry, this is me kind of messing around. So you can kind of imagine, like, as I move this beta 0, beta 1, right? Like we can kind of adjust. And what we're trying to do is just minimize that error and get it just right, right? That's essentially what we're doing. We do that twice, right? For like another linear regression on one side. Okay, let's go ahead and try to do a little practice here. So I'm going to load this data set, this wine data frame. So just kind of some quick notes on this data. So we're basically going to take this data here, and you can do all these different features. And basically it's that we're trying to predict the quality, which is like a rating for the wine. And you can see here, it's like, oh, how much, you know, fixed acidity, volatile acidity. There's some values in this, maybe it's percents or something like that. But the point is there's some numerical values. Red wine here at the end is just saying that is it red wine or is it not red wine? Okay, that's really what this last term is doing. Okay, so we're going to kind of skip over the exploration, but we could explore a little bit, kind of see like what features, if there's any cleaning we need to do, and kind of see like what features matter. We kind of skip over that. We can actually perform the regression. And so I'm actually going to use Scikit-learn because I like Scikit-learn better. So let me go ahead and just do this. So one thing that we can do, this is not a necessary part of linear regression, but it can be helpful just for us understanding. We can scale our data so it's not all over the place, and we can standardize scale it where everything's centered around the mean. And a value of 1 would be 1 standard deviation from the mean. It ends up being a little bit easier for us to kind of like also talk about it. We'll talk about this maybe over the next couple of study groups, but it helps us for interpretation to actually like be able to explain, saying, oh, like if you, for example, if you're talking to a non-technical stakeholder and you say, oh, if we increase, let's say for this wine, it's like if we have something is 5% more acidic than the average wine, we expect the quality go up to this level. That'd be kind of the way you could phrase this. So standard scaling is kind of a nice way for us to do that, because it's a lot easier for us to interpret and actually communicate our results to like non-technical stakeholders, and honestly technical stakeholders too, or just yourself. So anyway, I'm just taking this data here. This is actually coming from Scikit-learn. Ooh, let's see if I actually imported that. Okay, good. So this standard scaler is actually part of Scikit-learn, which is what we'll use a lot in phase 3. And you'll see me use this a lot for linear regression, because Scikit-learn is actually really great. But just know that this basically is scaling it. And what this does, the way this kind of functionality works in Scikit-learn, even when you're not really building a model, is you fit it, right? You kind of train your, what we call an estimator, which is what the standard scaler is. We're fitting it with our data that we have. So in this case, wine preds, I believe should just be, I just want to make sure I didn't run things out of order. wine. Okay, so we have our wine here. What I need is I need my predictions. So this right here is just basically just the targets, or sorry, not the targets, just the features. And this wine target is just the target that we care about. So wine price basically is everything except for the quality. Okay, so I got those loaded now. All right, make sense to everyone? Okay, so I'm kind of hopping around here, but kind of going a little more freeform. All right, so what we're doing here is basically taking our scalar and fitting it with the wine predictions. And basically what it's saying is like, hey, here's the data we're going to use to actually train the linear regression. Use this to define how we're going to scale all the values. So that's why it's called a dot fit. Basically, the scalar is learning how it should scale the values. And so that's what that dot fit is. And then to actually transform it, right, to apply that, process, we use our scalar dot transform wine preds, and that's just going to return a value. So if I run this guy now, let's see if I can show you wine preds. If I do that head now, you should see, oops, well, because it's a NumPy array. We can see here, like pretend this is our very first two values. Hope you guys don't mind me showing this stuff, like taking a little time. But you can see here is that this is our original values, like 7.4 is going to equate to this guy. Okay, 7.8 and 7.8. Oh, I think this is actually out of order in this case. But you can kind of imagine is that these values are now being scaled into, what's it called? Into by standard deviation, right? Is basically this getting shrunk down. So you can see these values are hovering, close to 1. Some values are a little bit higher, like this is a more extreme value, right? But you can kind of get the idea. It's like, okay, this is more positive or negative and stuff like that.
Hey, Victor, is all this scaling stuff, is this just normal packages within Python, or is this something we have to import to?
Yeah, this is actually from Scikit-learn, which is coming from, let's see here, this guy right here.
Oh,
so
cool.
from sklearn preprocessing import one hot code encoder, which we'll talk about next time in standard
Okay.
scalar.
Okay, thanks.
sklearn should be installed if you have the learning environment loaded. So you shouldn't have to do anything special. And it's a very common package you'll use in machine learning and data science stuff. Okay. And then you can see here, kind of looking ahead, we'll actually look at sklearn's linear model linear regression. That's going to perform the linear regression itself. And then filing the metrics for us to know how does it actually perform. Okay. So this is kind of like a little aside. Oh, go ahead. This kind of question.
So we did this is a standardization, right? But sometimes we also do normalizing, right?
Yeah.
What is the difference?
Yeah, sometimes people will equate normalizing and standardizing to be the same thing. One other way you could scale values instead of centering it around the average and then scaling it by the standard deviation, we could also normalize, or I'll say like min-max scaling, which you can say take the smallest value and the biggest value and scale it down to like 0 and 1. And in actuality, if you scale the features, it doesn't change the results of your linear regression performance. Your linear regression performance will be exactly the same, or it should be exactly the same, as long as you don't get some weird, funky like infinity values or something like that. But it'd be exactly the same. It's mostly for interpretation. So that's the real reason why we usually do standard scaling, just because it makes it easier for us to interpret the results of our linear regression. Does that make sense?
But then standardization will help for the model to perform better.
No, not for linear regression, I should say. For linear regression doesn't care. Linear regression is like, doesn't care if you zoom in, zoom out, squish, squeeze, all that stuff. It's going to be able to figure out the best performing line regardless. And that line should be the same performance. The parameters of that line will be different because you squished and squeezed the different values, but you'll see the performance of it is the same. For other machine learning algorithms, this is kind of important when we get into phase 3, some machine learning algorithms have to, or they perform better on certain scaled values. So looking ahead, like linear, neural networks, deep learning, which is a type of machine learning, values do really well and they're very close to zero, like when they're close to 0 and 1. Like you should scale down everything from 0 to 1, because values that are higher, which standard scaling could have something like 3, which is 3 standard deviations away. Neural networks don't do as well on those kind of values. But for linear regression, it'll perform the same. So, does that make sense? Cool. And to be honest, if I first introduced you, I probably would have skipped the scaling part right now because I think it's more like confusing right now. But so know that technically, tell you what, actually, I'm gonna do something scandalous here. I'm just gonna set this equal to wine preds. All right, we don't have like just to show you like it's gonna perform the same. But just know basically if you do scaling, you can feed in this value in here. So okay, pretend we scale it, didn't scale it. This is what you really care about. This is actually performing linear regression. And this is why I'm talking about like, it's more about the context versus doing the performance. These 2 lines will create your linear model. That's it. So you can see here, basically this linear regression is defining this model called, I call it LR here. Linear regression basically, okay, here's this LR and LR.fit. And this way, just remember that it's the same thing. You say, okay, here's all my prediction features. And here are my wine targets. So in this case, basically, here are my features, here are my targets, okay? And basically that trains it. It says, all right, it's trained. Real exciting, right? That's basically all of linear regression right here. So what this did basically, kind of breaking down like what just happened, is that it created, you can imagine like if we had y is the target, right? It's equal to, it defined what beta 0 is plus beta 1 times x1, and x1 could be like, for example, the fixed acidity, and there's a beta 2, or there's a beta for volatile acidity, and there's a beta for citric acid, and the beta for residual acid, and basically they have these all added up together, okay, to perform basically what is the prediction for y, and that's what this just did here. Basically took it, it's like, hey, here's all the data. How well can we make basically, how can we define our beta 0, our beta 1, our beta 2, and so on, so that this y is as close as possible to the actual target. Does that make sense to people? Okay, so again, to actually perform it code-wise, really easy. So I could have actually skipped that whole scaling thing and literally just said, all right, let me just get the wine preds, the wine target, and just feed that directly here. And that would be it. That'd be like maybe 4 lines of code. So you can see relatively quick and easy. But then you say, okay, like what were the actual coefficients? What were these beta 0, beta 1, all that? So we can do lr.coefficient, and this basically saying, hey, model, give me what those values actually are. And so this basically is built into the code for Scikit-learn for linear regression. It says, all right, show me the coefficients. And so each of these values now are the coefficients. This is the beta 0, or not beta 0, beta 1. This is the beta 2, the beta 3. And you can see here, if I look at like the length of this, so I'll just do that shape. You can see here there's 12 different values, right? Well, that's because there were 12 values for 12 different features. And that's where basically each of those coefficients are corresponding to each one of those features. Does that make sense? And then Scikit-learn actually keeps the intercept separate from everything. So the intercept, this is like the beta 0, it's 104. Okay. So I made a little thing right here. This is not necessary, but just so you can print it out. This would be the actual equation right here. It'd be y hat is equal to this values here. So x1 corresponds to, assuming that these are all in the same order, which I think they are, would be like fixed acidity, volatile acidity. Because I could just go like this. There you go. So you can see each one of these are corresponding to 0.09. So you can see here all these different values. And what you can kind of imagine is that because I didn't scale things, it's harder to interpret this. Basically, this number is, remember, this y hat's supposed to be the quality, right? Basically, this is interpreting to say, if we had all these values of 0, which I don't know if that makes sense, our quality would actually be 104 rating, which doesn't quite make sense. Like, I mean, I don't think that really makes sense in this case, because if you explore a little bit, the target quality goes from like 1 to 9. Like, so why is that going on? And partly it's because these values are all different scales. Some of these values, like total sulfur dioxide, are like in the double digits here. And then we have other things that are like really small, like citric acid. It's very, very small. So it's hard to tell exactly how do I interpret this other than the fact that it did well. So going back a little bit, like rewinding, like why we scaled. If I scale this, like this guy, just rerun this guy just to make sure we got it good. So now I have wine predicted scaled. If I run this guy again, where am I? Here am I. So this is going to create the same linear, like a linear regression model, but this time the features are all scaled. You can see here is that the coefficient shape's the same, but you'll see the y-intercept actually different. And in fact, if I look at the equation now, this equation is a little bit easier to understand. And so this is what I talked about, like, oh, it being a little closer to like actually interpret this. What this is saying is like, oh, remember y hat's still the quality, right? What you predict it to be. So this y hat in a lot of ways, if it had everything to 0, and what would be 0 for these values since we standard scaled it? If I put all of these to 0, what does that mean? That's a little pun.
Land.
You want to call it on.
It means the land. Oh, it's not a wine. Oh, it's not a housing data set. I'm sorry.
Yeah. So if these are all 0,
it's
after
an
we
empty bottle.
So if we standard scale it, since we standard scale it, these x1s, if I have x1 0, x2 0, x3 0, what does that mean? It means that when we say 0, it's the average. So it's the mean. Anyway, but so when we set everything to 0 in here, basically that says, okay, say the average fixed acidity, the average volatile acidity, average acidic citric acid, the perfectly average wine, basically, is what this is saying. If we set all these to 0, the quality would be 5.82. That's kind of the way you can kind of interpret this. And so you can kind of imagine now is that this first one, let's say fixed acidity, is that if we have, let's say we go up by 1 standard deviation in fixed acidity from the average, if we increase that fixed acidity by like 1 standard deviation, we would expect the quality to go up by 0.11. Does that make sense to people? So if I looked at, let's see if I can do this real quick. Getting all the rows, getting the first row, all the columns. This is fixed acidity. Oh no, that's the wrong way, sorry. That's fixed acidity. I should do np.mean. That's our value, and then our standard deviation. If I did this right, it's 1. Well, that makes sense, right? So we'd expect that 1. So let me just go back to wine preds, fixed acidity. So this would be the standard deviation here. So basically is that if I go up our fixed acidity by 1.3, we would expect 11%, or not 11%, a 0.11 increase in quality. So it'd be 5.82 plus 0.11, which would be 5.93. Does that make sense? Okay, and that's how you can interpret this. Which one of these values would I want to decrease from the average to increase my quality? You can just say x1, x2, x3.
Say that one more time.
The ones with the negative relationships?
Yeah, good. So we want, if the values that we want to decrease from the average percent, right? Like, so like citric, I think, let's say volatile acidity and citric acid, these are negative values. I would want to decrease our values, right? Or like from the average, and that would probably increase the quality of wine. Okay. So that's kind of how you can quickly look at something like this and say, oh, okay, I can kind of get an idea of like what this is. And what's really nice is that these values are kind of telling you the overall strength of like how much these values matter. So you can kind of see is that something like this x9, whatever x9 is that there's like a 0.08 increase when we go up by 1 standard deviation, right? So not a very huge increase, but if you look at something like, this value here, x4, if we go up by 1 standard deviation, we increase our quality by 0.3, which is, very like 4 times as big of an increase from here. So let's just pretend x4 is what 1, 2, 3, 4 residual sugar. That kind of makes sense. Well, I don't know if it makes sense. I'm not a wine person, but maybe making our drink more sugary would actually be a very beneficial thing to increase the quality. So this is something you talk to your non-technical stakeholders. Say, hey, like, turns out residual sugar is a big factor on the quality. So if we can increase residual sugar, that will boost we predict that quality will be boosted up significantly compared to if we try to increase what's 9 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we increase the pH, which I think that makes more sense too. If we increase the pH, it's not going to significantly increase our quality rating. Does that make sense?
I have one quick question. So if we went back to our main data and we got the mean of the quality from that original data frame, would that be 5.82?
Ooh, so you're saying the quality? Yeah, good. You know what, Safe? I think you got it, because that's actually kind of like my little knowledge check. Is that, so if I actually take the average of, let's say it was wine target, I think. Okay, and this is before it was actually like scaled and everything like that. If I do np.mean, there it is, 5.82. And that's exactly what's going on here, is that if we set everything equal, it just is the average from that wine target. Yeah, that makes sense to people. Hopefully that kind of ties together a little bit versus like just meaningless numbers. You can, if you didn't scale it, like what else we can do next is actually perform evaluation. So just show you a little bit, like R squared was the one that I mentioned about, saying, you know, how it compares. This is actually built into the scoring. And if I actually compare the wine Pred's target or scaled with the wine target here, we should see is our scoring here is a 0.296, so about 0.3. This, remember, is with, let's see, I want to make sure the wine target. Oh, this is with this linear regression. This is with it scaled, right? So just to show and prove to you all that like I'm not pulling a fast one and like making a scaling and it performs better. If I take this guy again, and so let's call this, instead of LR, we'll call this LR. I'll call it raw. So we're not going to scale it at all. So wine Preds. And again, to show you, just to make sure like I'm not pulling a fast one on you all. I'm saying like, hey, look, you don't have to scale it when you really should. You can see that this is not, nothing's scaled here. If I do this prediction here and then actually do, let's see, LR raw. So I'm basically using the non-scaled values with the wine target and then just showing what the score is for that raw. And if I have to put in wine Pred, since it's scaled, since we're using that, you should see the same value. In fact, you can see it's nearly the same, up to like any significant difference. In fact, I think it differs right here. It's the first time it differs from each other, which is basically negligible. Like essentially it's because probably these values stop at 7.4. And then when we scale them, like we saw earlier, is that those scaled values are like, I don't have it up here, but if you look at those scaled values, you can see that there's a lot more precision than it should be. Like you can see like 0.142473. There's not that many significant figures in these values. So that's probably where that difference is coming from. So essentially, these are essentially exactly the same, whether we scaled it or not. Okay, that makes sense to people? Okay.
I didn't quite catch what you're showing there. What is the thing you're changing between like what you're doing in line 34 versus 36?
Oh yeah, so this 34 was using, if I were to redo this, so all I'm doing is using the scaled values. And then let's just get rid of LR here. So what I'm doing here is basically taking linear regression and then fitting it on the scaled values and then seeing what that produces. In this case, it's the score is 0.3, right? So higher score, the better. So when I do this, I get this value. Well, if I didn't scale the values, I would still get the same score, even though the parameters would be different. So if I look at, just to again emphasize like the differences, like LR, that coefficients, you can see here, these are the coefficients for the non-scaled. And then, I'm sorry, for the scaled. And then these ones here, LR raw data coefficient. You can see here, these are the non-scaled values. So you can see the equation, the parameter is going to be very different from each other, but the performance is the same or practically the same. And
you're just showing that like, even though we scaled the values and changed the values by scaling them, we're not changing the actual relationship.
Exactly. So you're essentially just squishing things down, and linear regression is robust against scaling factors. The scaling will basically help you primarily just to be able to interpret it better.
So we would have to unscale it to apply it, like to a production?
Yeah, so one way you could do is you can unscale these values and basically get this raw coefficient. You could do it that way. One typical way you do it is instead you pre-process the values coming in. So there's new values coming in, you have your model trained that performs really well, you deploy it out, whatever that looks like, and you bring in new values in there, and these new values are going to look like these raw values unscaled. In your process, you would actually, to pre-process those data coming in, you would scale them and then feed it into your algorithm to make the prediction.
Okay.
Yeah, and that's where the idea of pipelines come in, which is Scikit-learn is really good at doing it. Simon, you had a question.
Yeah, one quick question. This coefficient value, are there some of the coefficients for each of the data point for each of the features, or like you have 12 features, right? And then you have a 12 coefficient, but then for each features has like 100 or 200 points. So these coefficients are summed, the average, or
You're talking about the score here?
the beta values, the coefficients.
Oh, the coefficients. So I'm sorry, can you repeat what was your question exactly?
So you have a one coefficient for one features, right? But then in actual calculation, is it just a one coefficient, or is it like a many coefficient for each of the data points? Like for example, each of the feature will have, let's say, there is 100 points for each of the features. Then your coefficient has to mathematically it has to calculate for each of the points, right?
Right. So these coefficients are determined from the full data we used with the dot fit right here, which is what this pred scaled is. So this coefficient is optimized. Well, all these coefficients together are optimized where the sum of squares in this case is actually what it's using to determine what the best fit is. And so we basically feed in all the data to our linear regression model, and that produces saying, okay, these are the coefficients that will optimize for the data that you gave me.
No, I understand that.
Okay.
I was just curious. Let's say if we have only one feature, only one.
Like one feature or one
yeah, and then
okay.
One feature will have, let's say you have 100 data points for fixed acidity, let's say.
Yeah, so
in actual calculation, is that only one coefficient, or I guess there is only one.
Yeah, so it'd still be one coefficient. Oops, I did this backwards again. Let's see, I see Eric, you raised your hand. If you had something to add to it, you can add to that. I'll get to you in a second. If we had just one feature, this would be like essentially fixed acidity. I could feed this into here as one feature.
Okay, yeah, I got it. Okay, if I think as a line, then it's just a one slope, right? Okay.
Yeah, I got to reformat, but I think you get the idea.
Okay.
Okay. Eric, you had a question.
Yeah, sorry. It's a little bit unrelated, but I know when you were kind of showing the full linear regression equation, it's like rounded to 2 decimal places. Is there anything going on with that? Because I feel like it may change. You know, if you want to have like, oh, here's the actual result or whatever, the resulting best fit equation. I feel like rounding may like drastically change what your residuals and stuff are. You know, as far as like, oh, this is like my best fit solution kind of thing. Do you have any like advice for that, or is that something to look at?
Yeah, so this one is this is a little function. If you guys are curious, I can show you guys what this is. This is just for you guys to display, and I just rounded it up to 2 decimal places, but that might be not realistic in a lot of ways. Like, for example, let's just say density has a lot of significant figures. I probably would want to include more significant figures for the thing for density versus like something that's like varies very differently. The biggest thing is going to be with the standardized scaling is that, as we saw, their difference does change. So like if you do care about these really significant, like just like small and minute changes, you have to be really careful about significant figures. For the most part, Scikit-learn, which is based on SciPy, does a pretty good job of doing that calculation for you. And that's because it's incorporated into the NumPy array. And the NumPy array contains basically those significant figures with its D type. So it kind of keeps track of like what matters, or like what precision you need. If you need more precision or you want to be extra careful, you would have to actually make sure that, like, for example, after I scale it, that this is not like, it's not 0.142473. I'd have to probably like reduce this number of significant figures so it doesn't round extra. But I think for reporting, for the most part, like for most cases, you probably are fine reporting like, something similar to this, maybe 3 significant figures in some cases, but I think this is relatively like this would be pretty typical, if that makes sense.
Yeah, I was just making sure that wasn't like, it was just like a display thing versus something precise or whatever.
Yeah, this is just a display, really. Like you could see the coefficients are actually like, these are the real coefficients, right? And you can see there's extra decimal in this case. And I just, for the record, like if I look at this like function, like I essentially am just I made it just for fun, essentially.
Okay,
yeah. So I just wanted to give you guys, versus me like showing the coefficients and then like talking about it, it's a little bit easier to read it like this. So.
I had one quick question. What is the LR dot score? What is that trying to tell us?
This guy right here? Yeah, so this is it's basically every Scikit-learn, because you'll later on find out that linear regression, we could replace this with other machine learning models to basically do this, and this .fit can actually take some time, and we can pass in extra stuff, including not just the predictions, or not predictions, the features in the target. You can pass in something called hyperparameters. That's we'll see later on phase 3. But the scoring thing basically is the way the linear regression model actually performs, saying how well this model performs. And in this case, the linear regression score for Scikit-learn produces the R² value. So capital R². So that's basically comparing how well this performs against, our model performs against the average model. So like saying, if we just said everything's average for the target, how well would it perform? And in this case, you can, there's a few ways we can talk about this. Maybe we can talk about this for future times too, because I know we're close to time, but you can kind of think it's being like, it's explaining 30% of the variance from that model. So, and in short, usually you want an R² value of close to 1. And close to 1, it depends on the situation. Sometimes 0.7 is perfectly fine. Sometimes 0.9 is not good enough, and 0.95 needs to be better. So in general, what this is really telling us is that there's a lot more variance that could be explained with 0.3. I would like, for most situations, 0.3, I would say I wouldn't feel comfortable putting this out in production. I'd be like, ooh, this model is kind of trash. But that kind of makes sense though, hopefully from this situation, is even with all these values, I probably would say there's probably other features that I'm not accounting for to predict the quality, predict the quality that someone says they are, right? So like, there are obviously things that are like, like where's like the bottle, the bottle is some kind of attributes, that probably does affect, how people rate the quality and stuff like that, whether we like to admit it or not, it's probably true. There's also person variation, are all the same people rating these wines? That could change the quality too. And that's not factored at all here, which I think this makes sense for the situation. I would expect 0.3 for R² to be pretty typical for what we were given. Cool. All right, I know we're at time, so but I think these are all really great questions, and I'm hoping that this is kind of a good setup. Like I said, like the actual performance of this, like you can see it's like, oh, you can copy those 3 lines and train away every single time. What's going to be really important is understanding the context of it and interpreting, this linear regression model. And next time we'll talk more about like what this looks like. I'll kind of a little preview is that so I talked about using Scikit-learn. You can also do this with stats models, and stats models gives a very robust output. So I'm just going to give you a really quick hint of that one, and then end it here. But I wanted to show you all what that looks like when you actually perform the linear regression with stats models. So stats models, when you actually perform the linear regression, it actually gives you a bunch of information about not just what the coefficients are, but also things like the t-statistic, the p-value. And this basically tells you whether or not, in this case, if this feature actually contributes significantly to the actual model, which is actually really important. So stats models actually builds it up together because stats models is very, as you can guess, very stats focused. You could do the same thing with Scikit-learn, but you have to build that yourself, essentially. You have to build out saying, how do I get the p-value, the t-statistic from this? And you can do it, but it just means you have to put more work into it. So StatsModel is kind of nice to put this out here. But Scikit-learn will be more relevant, or more relevant when we talk about more machine learning models, because a lot of machine learning models are built in Scikit-learn. So people who typically do linear regression with Scikit-learn and then say, okay, that was linear regression. Let me try it with a more advanced, more complex model. So that's why I want to show you guys that. Okay, cool. So next time, like I said, we'll continue on with multiple linear regression. I'll kind of go through this example of, like, what do all these values mean, or at least the ones that I think matter the most and that you really should pay attention to. And then also, my goal is that we'll have a little bit of competition. I'm going to give you guys a Kaggle competition where you can kind of like, it's very lightweight. You don't have to worry about it. I'll end it before we start up the project, but kind of just show you a little bit like, what that process might look like as you kind of adjust your model and trying to tweak it to better fit the data that you have. Okay.